Hi everyone! In this video, we are going to talk about the research findings from my Carnegie Mellon Robotics Institute Summer Scholars Program. Here, we propose a model-free deep reinforcement learning trajectory planner that exhibits safe, comfortable, and generalizable behavior on a wide variety of tasks. Traditionally, the solution to self-driving has been viewed as a modular pipeline that can be addressed in multiple parts. One such part is trajectory planning. Many trajectory planning methods have been proposed that don't use machine learning, such as a spline or lattice planner. However, since the cost function must be hand-engineered, it is difficult to generalize the approach to complex environments that involve large state spaces, other moving vehicles, and compound objectives. More recently, machine learning has made it possible to directly map sensors, such as RGB cameras, to actions, such as throttle, brake, and steering. These are called end-to-end systems. Shown here is one such end-to-end system that uses reinforcement learning. However, since deep learning is a black box, there are safety concerns using it to directly control a car. Furthermore, it has been observed that the resulting control policies are often jerky, as shown here. Hybrid approach seeks to use machine learning to map sensor data to a trajectory. We then pass that trajectory onto a non-machine learning controller to control the car. Past research has proposed imitation learning to plan a trajectory. However, the problem with imitation learning is that expert data must be hand-collected, which is a laborious task. Furthermore, the training data will likely not cover too many edge cases, such as near-crash scenarios. So we ask, what if instead we use reinforcement learning to do trajectory planning? And thus, I will present to you a reinforcement learning-based approach to trajectory planning. By using RL, the agent experiences many near-crash scenarios in its training and learns how to recover from them. Here, you can see the Ego vehicle driving in both static and dynamic environments, demonstrating passing behavior to overtake slow cars. So, how does RL actually plan points? First, the agent vehicle takes in an observation. Then, using the policy it's learned, it chooses a turn and acceleration, one tuple for each point it's planning. And using the bicycle model, it extrapolates this turn and acceleration over some constant time tau to find a resulting Cartesian coordinate and velocity. It then passes this point, or points, onto a PID controller to control the car. Reinforcement learning learns to minimize a high-level cost function. We choose a cost structure which discourages undesirable behavior, such as crashing, executing unnecessary actions, and violating the speed limit. The observation space that we present to the RL algorithm is a simplified representation from the environment. It is reasonable to claim that this information could be extracted from a perception module or incorporated directly into the RL algorithm, and we leave that open to future work. Here, we compare the performance of our trajectory planning method to a direct, control-based RL approach in our simulated environment. From these results, we show that our agent crashes less in a direct control-based method. Both methods were trained on the exact same observation space and reward structure until convergence. Here we see that our method results in less unnecessary lateral displacement in steering than a reinforcement learning controller. In the scenario shown here, we see that our approach is much closer to the expert level of driving. In fact, in the entire training, our RL algorithm interacted with only one simulated vehicle. However, in testing, we applied the agent in more diverse scenarios such as 2 or 3 simulated vehicles, and we see that our algorithm actually has continued improved performance over the direct control method. Well, here we are going to end. Thank you very much for watching this video, and I sure hope you enjoyed it.